So we're going to start off with circles. We have what we call central angles and inscribed angles. Central angle is where you have an angle in the middle. It is dead center, and this has a 90 degrees. So what we've learned about central angles is that the central angle is equal to the arc. This is the easiest one. Okay? Central angle is equal to the arc. So if this is A, B, and we just name a point over here, that means arc AB is equal to 90 degrees because that angle is equal to 90 degrees. Okay? So if I give you another one, let's say I give you this a little tougher one. Here's this circle. We've got a diameter. Remember that the diameter cuts the circle in half equally. So you have a semicircle, and with the semicircle you have 180 degrees. So here's a particular problem we had in class. And it may not be exactly perfect to scale, but we need to find these pieces that are missing. So as we look at it, this is all a central angle, so all the arcs are going to be the same as the angles. So if I look at this, and if I have my semicircle that goes straight down, so this right here is 180 degrees. If I know that it's made up of two pieces, I can take 180 degrees and subtract the 42 from it, and I can get that missing angle that's right here. So that missing angle is 138. Okay, so that's one side. Now I've got the thing I need to remember about central angles is their vertical angles. So vertical angles are congruent, and a lot of times with central angles you will have vertical angles. So that means that across from that 42, this angle right here is also 42. So I'm doing all the angles on the inside, and we'll come back and do the arcs. The arcs will be really easy. But if I want to find out how much that missing angle is that's on the left-hand side, this is also a diameter because it goes through the center. So I could take that diameter and know that this over here is 180 degrees. So 180 minus 64 and minus 42 will give me 74 degrees. So now I've answered all the parts of my angles, and what I like to do is name and number everything I can and then go back to look at the questions that are asked. So I've got everything labeled. That means any of those angles, their arcs are exactly the same. So we could just put these numbers outside on their arcs. And I have a circle that's totally complete that I could answer any question. If I wanted to answer the arc TQR, I would start at T. Let me do this in a different color so we can see it. I would start at T, I would go to Q until I got to R. So when I did that, I'm talking about everything that falls in between that arc of green. That means 64, 42, 138, and that's it. So I would add these together, and I would get 244 would be my answer. Okay, so central angles, you use a lot of semicircles and you use diameters to help you solve a lot of the puzzle to the pieces on this particular, on semicircles. All right, so let's talk about inscribed angles. So with an inscribed angle, it actually lies on the circle itself. It intercepts the circle, and it is inscribed angle has a formula that it follows, and the formula that we've given you is that the angle is equal to the arc divided by 2. Okay, so if I want to look for the angle, I have to take the arc and divide it in half. Well, if I'm given the arc, or I want to look for the arc, sorry, I take the angle and I multiply it by 2. Okay, so it just depends on what you're given. So if you're given that this is 25, now I know this is inscribed. It's no longer in the center of my circle. It is on my circle. So that means if I have the angle, I can multiply it by 2 to get my arc. So that means this angle intercepts this arc right here. It's inscribed. So it's double. When you go from a smaller area to a larger area, you multiply by 2. And if you go from that larger area to a smaller area, you have to divide by 2. Okay? So that's an inscribed angle. Let me give you some of the examples we may have. With an inscribed angle, what if we had a circle that had an inscribed angle but also had a central angle, and these angles shared the same arc? Okay? So if they share the same arc, they both hit this arc right here together. And what if you were told that this was 50? All right, this is a central angle. I just told you it was a central angle. So if that's a central angle, then the arc is 50. All right, but you've also got an inscribed angle that hits that exact same arc that you can now follow the rules. And the rule was, if you're given the arc and you go to a smaller area, all you have to do is take the arc and divide in half. So that means this angle that's inscribed is 25. Okay? That's one kind of problem. Let me see if I can find another one. How about we have a circle? I think many of you get this one. What if we have 2 inscribed angles that share the same arc? 2 inscribed angles that share the same arc. That means this inscribed angle hits right here, but so does this one. They both hit the same arc. So if that happens and you're told that this particular angle right here is 30 degrees, then you can double that because you're going to a bigger area and it's 60. But now, so if I look at the red, if I'm going from a big area to the small and I half it, I get 30. So notice that when you have 2 intercepted arcs that hit 2 intercepted angles that hit the same arc, their degree measure is the same. Okay? So that was something we worked on a little bit today. What if we had a problem that was, I had 2 intercepted arcs, they both hit the same arc. Okay? And one of them says I am 3x plus 2, and the other one says 40 degrees. And the problem says solve for x. So if you need to solve for x, then you got to figure out what's going on with these 2 angles. Well, if you notice, they're both inscribed. They both hit the same arc. So, oh, wait a minute, I know that I can set them equal to each other and solve. So if I do that, I subtract 2, I get 3x is equal to 38, and then 38 divided by 3 is how much? 12.7. Not very nice looking, but that's okay. I just made it up. So that means x is equal to 12.7. I could check my work. I could plug back in 12.7 and times it by 3 and add 2, and it better give me 40. So when I'm doing these kinds of problems, I can check my work and make sure that it gives you 40. It actually gives you 40.1. It's because I rounded. So that's okay. All right, so that's inscribed angles. We had a whole sheet on inscribed angles. What if I have a polygon that is inscribed in my circle? That means being inscribed in your circle means that actually every vertex hits the corners of the circle. So if I have this and I've been told that this angle is, do I want 89? let's say, yeah, that's fine, 89, and this one is 60. And you've been told to find x and y. What you need to remember that an inscribed polygon opposite angles add to 180 degrees. Okay? Opposite angles add to 180 degrees. So if this is 89, I can take 89 from 180 and get my y. So 180 minus 89 is going to give you 91. So your y is equal to 91. Well, you can turn around and do the exact same thing with the other two opposite angles. So 180 minus 60 will give you 120. Now, if on the test you were given 4 polygons, it's multiple choice, and you were told to find which one of them could actually be inscribed in the circle, you would have to make sure that those opposite angles add up to 180 degrees. It's as easy as that. All right, we can move on to another. I've got some worksheets sitting here. I'm just trying to decide what kind of problems to give you. What if I have a triangle? So we had a lot of worksheets lately that have had a triangle inscribed in your circle. So if they give you the fact that this is 90 degrees and they tell you that this is 120, we have to find, let's see, what are they looking for? They want to know the missing angle. They want to know this missing angle. Okay? So I'm going to tell you that this is actually a diameter, which makes sense because if this is 90 degrees, it has to hit the diameter. And it intercepts the arc. So if this is 90, this is an intercepted arc, this whole piece over here has to be 180. Well, that's a diameter, so that's a semicircle, which makes sense. All right? The next thing you need to do is make sure you're using all the information that they gave you. So they gave you that 120. Well, that 120 is actually an inscribed angle that intercepts this arc. So if I'm going from 120 down to a smaller area, all I have to do is divide it in half, and I get 60. Okay? If I'm looking for x, what do we remember about special right triangles? 30, 60, 90. Well, that automatically gives me that this is 30. Makes it easy. So x is equal to 30. I could have also gotten that from taking 180 and subtracting 180 from 90 and 60, which leaves me with 30. Okay? All right. So that's kind of inscribed angles as I'm looking through these sheets, trying to figure out what we've done so far. What if you have, many of you are kind of not remember about inscribed angles with a tangent and a chord. So, and actually, if I'm looking for this right here, and they give you the fact that maybe this piece over here is 170. That arc on the left-hand side is 170. But they're looking for this other angle. What do you know about a circle? A circle is 360 degrees. So I only have 2 parts to my circle, so all I have to do is take that 170, subtract it from 360, and when I do that, what do I get? 7, 8, 9, 190. So this arc to the right, all of this in the red is 190. So 190, 170 make 360, looks good. But now I need to know what this angle is. That's an inscribed angle. So I'm going to go inside, right? So that means I'm dividing that 190 in half. When I take 190 and divide it by 2, I get 95. So that angle right there is 95. Okay, inscribed angles. All right, let's do another one because this seems to be the harder one for you guys today. Here's another circle. I have a tangent that goes through here. I've got this, and I know that this angle right here is 58 degrees. But I want to know, what do I want to know? I want to know how much this arc is over here. All right, so what do I have? I have an inscribed angle, right? Inscribed angle. I'm going to double 58 to bring it out to my arc. If I do that, I can find out how much that missing arc is. So this is 116. Now we have two parts to our circle, and a circle is always 360. So I can take 360 and subtract it from 116, and I get that missing arc that I actually need. So for this arc, it's 244. Now, okay, all right, Miss Williams, what if I wanted this second piece of information here? So if I'm given 244, I can divide it in half to get this other missing angle. And there I've solved my pieces on my intercepted arc, my inscribed angle. All right, let me go to, we had a couple sheets. One of them was called the tangent radius theorem. And that is when a radius drops to the circle and is cut by a tangent, it will always create a 90-degree angle. So with that, we learned that a whole lot of triangle stuff goes on with that 90-degree angle. So if one side is 90 degrees, then the other side is also 90 degrees, correct? So if I have a triangle, if I want to find a missing angle, and I was given that this was 32, and I had 32 and 90, you have to remember that you just take the 32 and the 90 and subtract it from 180, and that will actually give you that missing piece of your triangle. So this angle would be 58. Okay, so a radius intercepted at the circle with the point of tangency, that point that it hits the radius, the tangent and the radius is the point of tangency, creates that 90-degree angle. Okay, remember that? Creates that 90-degree angle. All right, I'm going to have to cut this into 2 videos because I'm about out of time this afternoon. The bell's about to ring. So I will remember that I have done the tangent radius theorem, and I will try to do some more problems tomorrow. Thanks.